In this last lecture of the introductory part of this course, I'm going to talk about sampling algorithms, and this will prepare you for the actual computational based work that Bruno will teach you about. Okay, so if you recall, in the previous lectures, I had covered two simple analytical cases, the beta binomial conjugate case and the Poisson gamma conjugate case, right? And so in each of these cases, what happened was that the posterior that we got of the theta parameter in the binomial and the theta parameter in the gamma, the posterior always had analytical form, and that analytical form in the beta binomial was a beta distribution, and in the Poisson gamma, that analytical form was a gamma distribution. And what that means is that because we have an analytical form for the PDF of the posterior distribution, we can easily summarize it graphically, right? We could draw the shape of the distribution graphically, and we can describe the uncertainty of these estimates with, for example, a 95% credible interval or something. So that's how we can summarize the properties of the posterior distribution, because we have the closed form PDF, right? So even in R, we could use the d beta and the d gamma distribution, the d beta and d gamma functions to summarize the shape and the properties of this distribution, namely the mean. By properties, I mean the mean and the lower and upper bounds of some kind of credible interval, which marks the range over which we are 95% sure that the values lie. Now, this is all very well and good in these analytical cases, but in real life situations, what will happen is that we will encounter much more complex situations where we can have as many as 40 or 50 parameters. We're not talking about one parameter anymore, right? And in that case, it becomes extremely difficult to figure out what the analytical form of the posterior distribution is. Moreover, even if you figure it out, there is no built-in function like d gamma or d beta that allows you to work out the properties of that distribution, right? So you're going to have to figure out somehow. You will have some complicated likelihood function, and you'll have a long list of priors, right, which you'll have to multiply with the likelihood. And this will give us, in principle, the posterior, but there is no analytical way to compute it in realistic situations. So the problem we are left with is that we have the prior specification and the likelihood. We have to work out the posterior up to proportionality, and we need to, instead of looking up some analytical form of the PDF, we are going to have to somehow get samples repeatedly from this posterior distribution so that we can draw the posterior distribution as a simulated set of samples. And with those simulations, we are going to now summarize the properties of that posteriors. For example, the mean and the lower and upper bound of the lower and upper bound of the credible interval, right? So that's the real goal here. Okay, so how do we proceed? There are several ways to obtain the posterior in this way. So I'm going to show you some of the classical approaches, and then I'm going to give you a very superficial summary of the actual sampling approach taken by Stan, right? So there's not enough time in this course to actually get into the full details of the sampling algorithm used in Stan, but I'll give you a flavor and some example code that shows how the whole sampling procedure works in Stan. But first I will start by introducing the simplest ways that one can obtain samples from some PDF. Okay, so the simplest example or the simplest method for obtaining samples from a posterior distribution is to take the PDF of the posterior and then simulate from this posterior in the following way. Right? So first what we have is what's given to us is the PDF of this distribution of some posterior distribution. Okay, so maybe I should write it like this: f of theta. Let's say theta is our parameter, and we have the PDF of this distribution. If we want to sample from this distribution, right, what we're going to do is we're going to first take a random number u from a uniform distribution with range 0 to 1. So what we are doing is we're taking one number between 0 and 1 with equal probability. That's what a uniform distribution looks like. Okay, so we get one number u from a uniform 0, 1 distribution, and then we equate that random number to the cumulative density function of cumulative distribution function, of this PDF. Remember in the foundation lecture, I told you that there was a correspondence between the PDF and the CDF, right? So CDF's written something like this, for example, right? So if you have a PDF like, let me just get back to my notes here. If you have a PDF f of theta, let's say, that looks like this, right? This is my theta. This is the PDF associated with theta. I can actually figure out the probability of observing some value like z or something less than that, right, on this x-axis, some value z for theta or something less than that by calculating the area under the curve, right? And the cumulative distribution function actually achieves exactly this. So what it does is you can rewrite this PDF as a CDF. So what we can do is we can draw it like this. So different values of theta will have different probabilities, and we can basically look up in this CDF. If we look up this value here and go to this point in the figure, this gives us the probability of observing this value, let's say z1 or something less than that. So f of z1 is this value here, right? That's what the CDF does. Right? This is just a way of plotting the cumulative distribution function and basically computing this area under the curve, which is the probability, and that probability will be this number here on the y-axis. Okay, so that's how we represent the PDF and the CDF, right? So why was I talking about this? What I'm talking about here is that we have sampled a random number from a uniform 0, 1, and we equate that to the CDF of the particular random variable we are looking at, right? So what does that mean? Graphically, what does that mean? It means that I have some CDF for my parameter theta, 0 and 1 here, and so these are maybe low probability values and these are high probability values. This could be one distribution, cumulative distribution function corresponding to some PDF, right? So what I do is I take a random sample from somewhere between 0 and 1. It could be this point, it could be this point, this point, or this point, all with equal probability because I'm taking a sample from a uniform 0, 1 distribution. Okay, so the interesting thing now is that this distribution that I've plotted here is the f of z for different values of z on the x-axis. Okay, so basically what I'm doing is I'm going backwards in this figure. I will take a random sample, let's say this one from a uniform 0, 1, and I go to this figure and I figure out what the z value corresponding to that random uniform number that I sampled is. Okay, so what is the value on the on this theta axis, on this x-axis, which represents theta, what is the value on the x-axis that corresponds to this random number that I sampled? Okay, so what will happen is the following. I'm randomly sampling from numbers between 0 and 1, and so what that means is I will get with equal probability values between 0 and 1. That's what a uniform distribution gives me. But because of the shape of the CDF, what will happen is that the CDF will have a shape like this, and what that means is that most of the time I'm going to land in this region here, right? So I'm going to, most of the values that I will sample randomly from the uniform distribution will land me in the center part of the theta distribution. And what that means is it'll be only very rarely that I will get a value like this one or a value like this one, right? So these extreme values will be rare and these central values will be more common. And that is exactly what a normal distribution or this typical distribution that we see in many cases will have. Most of the density is concentrated here. That means most of the values are coming from the central region, and only rarely do we get values from the edges of this distribution, right? So that's what this procedure does. You take a random sample from a uniform 0, 1, equate it to f of z, and then solve for z. Okay, so this procedure actually requires some calculus, which fortunately for us we don't need to know. We just need to understand the procedure graphically, and I think I showed it to you here, right? So to give you another example, right? So if I had a CDF that looked like, let's see, if I had a CDF that looked like this, okay, what would happen now? What would happen is that most of the values that I would get samples for would be concentrated around this part here, because you can see that every time I get a sample from between 0 and 1, I'm going to get values very near this point here, right? And it's only rarely that I will get those extreme values. So this kind of CDF actually corresponds to a PDF that has this shape, this skewed shape. Okay, so that's why this method works. This method is called the inversion method. The inversion method, and what we are doing is we are taking the CDF, sampling from a uniform distribution between 0 and 1, and then mapping back to the x-axis, right, like I showed you graphically. So that's basically what this approach is. And so I'm going to do this now and show you for the normal distribution, right, how I would take samples from the normal distribution. Remember that actually I don't need to do this crazy procedure to sample from the normal distribution because I have the R norm function. The R norm function in R will give me, for a given mean and standard deviation, will give me samples of whatever size I want from this distribution. So I don't need to do this inverse sampling, but I'm just doing it because I want to illustrate it with a case that we understand very well. Okay, so in the case of the normal, the probability density function of the normal distribution is the thing that we learned about in the foundations lecture. Oh God. And the corresponding CDF, so the normal distribution looks like this, and the corresponding CDF will look like this, something like this, right? So what we do is we take a random sample from a uniform, so one random sample, and then we take that U value and we push it through the Q norm function. The Q norm function, remember from the foundations lecture, is the CDF. This is why I spent so much time on the foundations part of this course, because this is the moment where there's a payoff. If you know what a P norm function, I'm sorry, I just made a mistake. So it's the inverse of the CDF, right? Q norm is the inverse of the CDF. So this is why I spent so much time. I always get confused about this when I'm actually teaching. But so we have the likelihood function for the normal, the D norm. The CDF of the normal is the P norm function, right? So this is the CDF. That's this function here that I showed you. And the Q norm function is the inverse of the CDF. And that's basically this plot here flipped over. So if this is X here and this is the probability, right? the Q norm function puts probability on the x-axis and the x's on the y-axis, right? That's why it's called the inverse of the CDF. And the function in R is Q norm, and we did some exercises on this earlier, if you remember, right? So given some probability U, it's going to give me back the value of the random variable that probability corresponds to. So basically what I'm getting here is the f of 0.87794 is actually whatever the value of U happens to be, right? So that's what I'm getting here, right? And this is the probability now of observing 0.877 or something less than that, right? So if you remember the foundations lecture, that's how this is all set up. All right, so this is why it's so useful to understand what a distribution is, what a PDF is, what a CDF is, and what an inverse of a CDF is, right? This is where the payoff is, because it allows you to do inverse sampling very easily, right? So right now, of course, I'm using a silly example. I'm using a normal distribution, which we already know how to sample from. But suppose it was not a normal distribution that we were looking at, but some other distribution, we could still do inverse sampling as long as we can solve for Z. Okay, so instead of Q norm, we'll be doing some analytical work. I will show you an example in a minute. So the second example is sampling from the standard normal, right? So this is not a second example. This is just the same example I showed you just now. I'm getting 10,000 samples from the standard normal by repeatedly, so 10,000 times, I'm repeatedly generating a random number between 0 and 1, then using the QNorm function to save my sample in each of these cells of this vector called samples. And this vector will contain 10,000 samples of a normal distribution with mean 0 and standard deviation 1. Because I'm sampling from this, I'm solving this inverse CDF here, right? And this inverse CDF refers to a standard normal distribution by default. In the D norm, P norm, and Q norm family of functions, if you don't specify the mean, and the standard deviation, it's by default assumed to be mean 0 and standard deviation 1, right? So that's why I'm getting samples from the standard normal here, okay? All right, so this is what if I draw a histogram of that vector of 10,000 values, I indeed get a normal distribution with mean 0 and standard deviation 1. Another example is sampling from an exponential or gamma distribution. This time what I'm going to do is I'm again going to take repeated samples and each time take a sample from a random from a uniform distribution with minimum 0 and maximum 1, right? And then instead of using the QNorm function, I can use the QX function for the exponential distribution and get samples from that distribution. And that's what it looks like. So you can see the classic exponential shape here with the rate lambda equal to 1 here. I think that's what the default is in the QX function, right? Similarly, gamma distribution. Instead of using the QX function, I'm using the gamma distribution with A and B parameters set at 1, okay, just as an example. And this distribution again has this characteristic shape that is actually a gamma 1 1 distribution, okay? All right, so these are all easy cases because I mean these exponential gamma normal cases, we already know how to sample using the R family of functions. But now suppose that I gave you a PDF like f of x here, where I've got some particular definition for the PDF which you've never seen before and for which there is no function in R. So now you're stuck. There's no way for you to obtain samples from this distribution. Okay, so let's assume for simplicity that the support of this random variable is that it ranges from 0 to 5. Okay, so if I plot this PDF, it will look something like this. Okay, that's what this PDF looks like. The x-axis ranges from 0 to 5. All right. So now we don't have any Q family of functions to use inverse sampling with. So what we're going to do now is that, as before, we're going to take a random number from the uniform 0, 1 distribution, and then what we're going to do is we are going to equate that random number u to f of z, the CDF of that distribution, and then we are going to solve for z. Okay, so I'm not going to do the calculus to show you how this is done because it requires a background in calculus and we are not assuming that in this course. So basically what will happen intuitively is that I will write u, and then there will be some expression here that is a function of z. Okay, there will be some expression here that's a function of z, among other things. And then what I will do is I will just do some simple algebra to figure out what z would be with respect to all the other variables that I have here, right? So basically I just solve for z here, and that gives me the inverse of the CDF, right? This gives me the inverse, effectively gives me the inverse of the CDF for when I repeatedly sample from this uniform, right? So it just turns out that if I do this, if I solve for z, this is the expression that I will get. I didn't show you how to do this, but this is a combination of simple calculus, integral calculus, and some simple algebra after that. You have to complete the square and so on. But those details are not important. What's important is that I've solved for z, and now once I have a sample from u, I can now produce a z, because everything else is known in this equation, in this box here, right? So the problem with this method, of course, is that if we can't find the inverse of the PDF f of x, then there's nothing we can do, right? So we are kind of stuck here. Also, it can't be used with multivariate distributions where you have multiple variables involved. So this is a very limited method, but if there is one parameter involved in a distribution, such as the example 3 that I'm showing you here, there's only one parameter, which of course I've confusingly called x. So don't be confused here. Right now, when we're talking about the posterior distribution of some parameter, let's say theta, then this f of x would actually be written f of theta, right? I just happen to be using the variable x here just out of habit, but it's this is not this shouldn't confuse you, because I'm talking about the posterior distribution of some parameter. So if I have a single parameter, I can use inverse sampling to work out to get samples from that for that parameter. Okay? But it's a very limited method. So what do we do when we have more than one parameter that we want to estimate? So for example, if we want to get a posterior distribution, not just for the theta parameter in the binomial, not just for the theta parameter in the Poisson likelihood. Suppose we want to get the posteriors of the normal distribution for the mean and the variance. Now there are two parameters, right? So now I can't use inverse sampling. So in those situations, Gibbs sampling is a very commonly used method. It's the classical approach, in fact. And the way it works is as follows. Okay, so we're going to represent the vector of parameters with big theta here, right? So theta, this big theta is intended to stand for theta 1 and theta 2, let's say, right? The two parameters that I'm interested in. Now this is going to scale up quite easily, right? So I could have 20 parameters instead of 2. And in these complicated linear mixed models that we will fit, we will have 20, 30, 40 parameters in the model, even more, right? Okay, so here's a situation where I've got a vector of parameters, right? And let the number of parameters be k. Okay, so the length of big theta is k. And what I'm going to do is j is going to index the iteration in the sampling algorithm. So j will be, let's say j will be step 0, step 1, step 2, and so on. So if I decide on running the sampler for 10,000 steps, 10,000 iterations, then this jth term will be iterated, will be increasing in value each time. Okay, it will be representing the jth iteration, sorry. All right, so the 0th step of the sampler assigns some random values to each of the parameters. Okay, so that's what this starting point is. Then we update the iteration number. So we say that we are going from step 0 to step 1. And then what we do is, so I want to consider this situation again, this bivariate situation where I have two parameters theta 1 and theta 2, right? So there will be some joint distribution for theta 1 and theta 2, right? It's a bivariate distribution. There are two parameters and there will be a bivariate distribution. If you remember, we discussed this a long time back. So we talked about a situation where we had two random variables, right? So call this theta 1, call this one theta 2. So here we are seeing this smooth cone is smooth from all angles, which is describing the bivariate density of this distribution. So really this is the joint distribution of theta 2 and theta 1. Now it turns out we can easily work out in this situation the conditional distribution of theta 1 given theta 2 and the conditional distribution of theta 2 given theta 1. What that really means is, what I want to know is the distribution of, for this first term here, the conditional distribution of theta 1 given theta 2. What I'm going to do is, I'm going to take one slice from theta 2, from this side. I'm going to take one slice through this distribution, right? What that will give me is a flat plane in this bivariate distribution, in this cone. If I take a cut from one side, I'm going to get one flat plane. And if I look at theta 1 from this side for that particular slice that I took from the theta 2 angle, right, I'm going to get a univariate distribution that is a conditional distribution of theta 1 given theta 2. Similarly, I could flip x1 and x2 and get the conditional distribution of x2 given x1, right? So that's what it means to have a conditional distribution from a bivariate case. Okay, so where was I? All right, sorry, I wanted to get here. Right here, right? So what I'm going to do is, I'm going to take a sample for theta from the conditional, using the conditional distribution of theta 1 given theta 2. I'm going to take one sample, right, by using the previous value of theta 2, which I had set in the 0th iteration. I just put some random value for theta 2 and theta 1. I take that random value from the previous step for theta 2, plug it into the conditional distribution, and I get a sample for theta 1 from this conditional distribution. That's this step here. Similarly, I'm going to produce a sample for the second parameter, which is theta 2, given the value that I just generated for the other parameter in this current step, right? So I just generated this. So let me say that I saved some value theta 1 here. I'm going to plug that value theta 1 here and generate the distribution of theta 2 given this particular value of theta 1 using the conditional distribution that I derive analytically for theta 2 given theta 1, right? So that's how I get in the first step. Now I started with step 0, right? In the next step, which is step 1, I get one sample each of theta 1 and theta 2. So I keep repeating this process, right? From the I use the conditional distributions of each of the parameters to get a sample for each of the parameters using either the preceding steps theta value for the first parameter or the current generated theta value for the second parameter, just as I did over here. Okay, so that's what Gibbs sampling does. You repeatedly keep sampling from the conditional distributions for each of the two parameters, and eventually you end up with the posterior distribution. So intuitively this should make sense, right? If you look at this here, so intuitively what's happening is that what do I want to say? Yeah, intuitively what's happening is that, let's say this is called theta 2 and this one is called theta 1. If I fix this point and take a random sample from this distribution, then I repeatedly keep sampling in this way, I will eventually get this distribution, the marginal distribution for this parameter. And similarly, if I keep walking up and down the theta 2 parameters range and try to get a sample from the conditional distribution for theta 1, given different values of theta 2, I will eventually get the distribution corresponding to theta 1, right? So that's how I end up with samples in Gibbs sampling from the conditional distributions. Okay, so here's an example. Okay, so imagine that I have a bivariate distribution. This is not a normal distribution. This is just some bivariate distribution, right? You could actually draw this in a three-dimensional figure. So that's a good exercise for you. Just take this bivariate function, push it through a three-dimensional plotting function in R. There are several of them available, and you will see what the shape of this bivariate distribution looks like, as long as you define some range of values for x and y. Okay. All right. So it says here, using the methods discussed in the foundations chapter. This actually refers to a much more extensive course over 13 weeks that we teach. So we have not taught you any of the calculus that's needed for doing all this work. But if you already know calculus, once you know this joint distribution, you can figure out the conditional distribution of x given y and of y given x. So we have given you the solution here. Okay. So you can certainly work this out analytically. It's actually not very difficult, but it just needs some background in conditional probabilities and in solving some equations. Okay. All right. So where was I? Yes. So we now have the conditional distributions for both the parameters x and y, right? And so the Gibbs sampling algorithm will work like this. Now we set some initial random values for x and y. I just came up with some numbers, okay, -5, and step j is 0 right now. Okay, so now what we're going to do is, in the next step, j plus 1, that means step 1 now, we're going to sample x from the conditional distribution of x given y. I just showed you what that distribution was, right? And we will do that using the method we learned earlier, which is inversion sampling. Remember that we now have a particular closed form statement for a univariate distribution, the distribution of x given y. Okay, so that means that we are now in a position to use inverse sampling to figure out how to generate samples from this. Okay. All right, so to do that, to do inverse sampling, we're going to have to figure out the inverse of these conditional distributions, right? So that's why you need calculus now. I've got some conditional distributions. I'm going to have to use some calculus to figure out the inverse. I'm not going to make you do that, but one can do it. And so basically now what we do is we generate a random number between 0 and 1, right? And then we basically solve for the quantile, solve for z1, just like we did earlier. Basically all we are doing here is computing the CDF of that of the conditional distribution and solving for z1. And similarly for the next term, what we do is we generate a random variable, and then we take the conditional distribution, the cumulative distribution function for the PDF of y given x, and then we figure out the value for y as well. Okay, so in each case you'll notice that there are two variables involved here, right? So what you're going to do is, when you're using the CDF of x given y, you're going to use the value of which value of y are you going to plug in here? You're going to plug in the value from the 0th step, the one that you randomly generated here. So that is -5, right? But once you have run the Gibbs sampler to produce a sample that is z1 of the x value, so x is in this current step 1, x is now z1, right? So what you're going to do is you're going to take that number, whatever that number z1 is, and plug it in here, and then solve for z2, because you right, and then you solve for z2, and then you get you get a sample from the conditional distribution of y given x. So this is how it proceeds. You keep repeating this process now. Instead of once you've gone to step 1, then you go to step 2, and so on, and repeat exactly the same thing. Here's the code for what I've just told you. We're going to run 2000 iterations, and we're going to save the samples of the parameters x and y in a vector with 2000 cells in it. So here's the initialization in step 0, and notice that I start with step 2. The reason is that the vector x and y has 2000 cells, and confusingly for us now, the first cell in this vector corresponds to step 1, which for us is step 0. This was initially algorithmically it was step 0. So this is a historical confusion in computer science, we tend to start with 0 as our first count, not 1. And so that's why often you will see the starting point of the algorithm, as you saw somewhere here, right, with j is equal to 0. That's probably an artifact of the fact that in computer science we always start with the 0th count, right? So don't get confused about this. So what's happening is that in step 1, so I should not have said step 0. So in step 1 we have initialized the values, and from step 2 to 2000 we're going to carry out the steps that I told you earlier. We're going to use inverse sampling to get a sample for x, for the parameter x, by using by basically solving for z after having taken the random sample u, random value u from a uniform distribution, right? And similarly, when we're getting a sample from the conditional distribution of y given x, we're going to generate a random number between 0 and 1. And for the conditional distribution of y given x, we're going to compute the CDF and then solve for z2, and that z2 will be our sample for y, right? So these long and complicated terms that you're seeing here, these are this is the inverse of the CDF, right? So this you can do analytically if you have enough patience to work through it. You can work out the analytical form of the solution for Z1 and Z2 once you've got the CDF, right? Okay. So when you run this code, you should try to run this code later on, okay? And when you run this code, and you can plot the simulated posterior distribution, the joint distribution, and that's shown here. That's this distribution here that I produce using this function here, KDE2D from the mass library. I'm producing the joint distribution of x and y. I'm drawing it with a perspective plot, right? So you can see that this is what the joint distribution of x and y looks like when you sample from these distributions. You should also, as an exercise, if you feel like it, try to draw this distribution, okay? And it should look a lot like this distribution here, okay? All right, so now the basic insight in this method of Gibbs sampling that I showed you is that we have to be able to figure out the conditional distribution in the case where we have multiple parameters that we want to sample from, right? Let's say I gave you an example of 2 parameters here. I'm going to have to figure out the conditional distribution of theta 1 given theta 2, and the conditional distribution of theta 2 given theta 1, and this will allow me to simulate from the joint posterior. It's magical, right? It's amazing that you can actually get the joint posterior from the conditional distributions. Okay. So there are other methods also, more sophisticated methods for doing obtaining samples from a particular distribution. So one other approach is the following. So the kind of situation I want you to imagine is that you have some complicated posterior distribution like this that you want to sample from, right? So what you do is that we first start, so let's say we have some parameter theta that we want to, so this is on this x-axis, I have theta here, and I want to obtain samples. Basically what my goal is actually that because I have a peak here and a peak here and a peak here, there's a multimodal distribution, right? So what I want is in the high density regions, I want lots of samples from here and here and here to accurately reproduce this distribution. I only want occasionally samples from here, and I want less frequently samples from these low density regions, right? So really what should happen is that I should very often get samples from here, here, and here, from where the peaks are, and somewhat less frequently from here and here, and very rarely from the tail of this distribution, and here and here. Okay, that's my goal if I want to get samples from this distribution. So what we do is we're going to repeatedly carry out, for multiple steps, we're going to carry out the following approach, right? This is called random walk metropolis. What we do is we start at some random location on this x-axis. So let's say I start here, okay, just by chance. I just decide to start from there by chance, by just randomly choosing that point, okay? And then what I do is I propose a new location using some other distribution. So imagine, that I could have defined a uniform distribution like this, right? And I could say, okay, I'm going to use that uniform distribution to propose a new move on this x-axis. I can propose a new move to, for example, here, by getting this value and then mapping it to this point here, okay, something like that. So I can propose a new location in this way by using some other distribution. And then what I do is I calculate a ratio of the two posteriors, right? So what I have is, in the ith step, where am I? Yeah, in the initial step that I had taken, which was step I had some proposal for theta 0. This was randomly generated initially. What I do is I take my likelihood and plug in that random value in step 0, let's say, and multiply that with the prior on theta, okay, which I will of course have specified. And so I multiply this to get a posterior, a value that's the product of the likelihood and prior, and I compute the ratio of this, let me just call it the posterior, because it's the product of the likelihood and prior, okay? So I'm going to compute the ratio of this posterior for the newly proposed value versus the old value that I had for the theta parameter. Okay, I've just proposed a new location, remember? So I proposed a new value. So I compute the posterior for that posterior value that I get with the new proposed location, and compare that to the posterior value I had from the using the previous value of theta, right? So what this gives me is a ratio, right? It gives me a ratio of the two posteriors. And then what I do is, again, I generate a random value between 0 and 1. If my ratio happens to be bigger than u, what that means, as I will just show you graphically, is that my new proposal, so the numerator here in this ratio here, the new proposal, theta I plus 1, is moving me to a higher density region, okay? So basically what I'm going to do is I'm going to probabilistically make a move to that higher density region. It's not necessary that I will make a move to that higher density region. Why? Because this u value will be randomly generated. It could turn out to be greater than the ratio. Okay, it could. So probabilistically I will make a move to the new location, the new proposed location on the x-axis. Otherwise I will not make any move. So let me show you the graphical intuition to this. Okay, so suppose I've randomly started at this point, so that's why I've got this point here. So what we do is we propose a new move to this point here, right? This is my proposed location. I've proposed a move to this location. Let me try to erase this. I want to how do I do that? Just a minute. I'm not very good with this technology. Right. So what I really want to say is that I've proposed, this is just a proposal, so I won't say that this is this is something that I've actually done yet. I've just proposed moving to this point here on the x-axis, right? So what I do is now I compute the ratio of the proposed to current likelihood times prior, like I showed you earlier. Now if I compute that and I get a smaller likelihood here, right? Likelihood ratio really, right? So this is actually can be seen as a likelihood ratio that I'm getting, right? So if I get a lower value here, so let's say 0.83, now I'm going to use that ratio to decide whether to probabilistically move from this point to this point. Okay, I'm going to decide now. How do I decide? I decide by taking a sample from a uniform distribution between 0 and 1, and this could be any number between 0 and 1. It doesn't have to be 0.9 like in this example, but suppose it was 0.9. In this case, 0.9 is bigger than 0.83, the ratio, and therefore what that means is I'm going to end up staying in the current location, because we only make a move if the likelihood ratio is larger than u. Right? So in this case it's not. If u had been 0.8, then I would have probabilistically moved to this location. From here I would have moved here. Okay. So I would have taken a sample from the theta parameter, right, from here now, if the u value u had been 0.8, let's say. Okay. All right, similarly, suppose I'm starting at this random point here. This is my starting point in the algorithm, and suppose the proposed move is to this point here. Okay, so this is now a proposed move. Okay, so now when I compute the likelihood ratio as before, I get a value bigger than 1. I'm moving to a higher density region. I'm actually moving to a higher density region. In that case, what will happen is that I will always move to this new location, because the ratio, which is 1.33 here, is going to be greater than 1, and this ratio will always be greater than 0, no matter what what will be always greater than u, no matter what u happens to be, because u can only u ranges from uniform 0 to 1, right? So u can never be bigger than 1. So this condition is satisfied. So whenever whenever a proposal is a move to a higher density region, that move will happen. Okay. So this method is an alternative to using Gibbs sampling. In fact, Gibbs sampling is really a special case of an algorithm called Metropolis Hastings, which I haven't discussed really in this presentation, but I hope I've managed to give you an intuition for how sampling algorithms work, right? Okay, so it turns out that the big deal with STAN is that it actually uses a very efficient sampling algorithm called Hamiltonian Monte Carlo. And basically what this approach does is, I will not discuss the details of this approach much, because this would at least take me at least another 45 minutes, and I think that it's not enough time to give you a really good understanding of the Hamiltonian Monte Carlo method, and besides, there's not enough payoff in fully understanding it right now. Maybe once you get deeper into Bayesian analysis and you want to understand the underlying machinery, you should study this in more detail, but I'll give you the quick intuition for this. Okay, so basically the idea that you want to think about here is that, suppose that I am trying to sample from a distribution like this, a simple distribution like this. What we're going to do is we're going to flip this distribution over upside down, take a mirror image of this distribution. Well, that's supposed to be a mirror image. I'm sorry, I didn't draw this very well. And basically we're going to imagine that we have a ice puck, that we're going to hit on a frictionless surface, and that ice puck will move along this space here, right? And so you can imagine what will happen with an ice puck that is moving on a frictionless surface. It will end up landing in this region more often than in these rare regions. It will visit those regions more rarely. As a consequence, what will happen is we'll get many more samples from this part and very few samples from this part, which is exactly what we want, right? So that's basically how the HMC approach is going to work. Of course, I'm simplifying this ridiculously, but I think this is okay. So one limitation of the approach that we have with HMC, with Hamiltonian Monte Carlo, is that it only works with continuous parameters, so not with discrete parameters, but Gibbs sampling can handle that. So you can always move back to Gibbs sampling. And if you ever need to use Gibbs sampling or Gibbs samplers for your work, I advise you to look into the literature on the JAGS software. And there's a very good book by Lunn et al. That I would advise you to read if you want to use the JAGS software for using Gibbs sampling. This is called the Bugs book. This is a classic book that covers most of the commonly used models, right? But the big advantage with STAN over JAGS and over any kinds of Gibbs sampling is that when you have very complex linear mixed models or hierarchical models, you're going to have a lot of parameters that you need to estimate, and Hamiltonian Monte Carlo will get you there much faster and more efficiently than Gibbs samplers. Gibbs samplers will not be able to give you estimates from all the parameters in finite time. I think it's been my experience at least, and they really don't scale up very well for the very complex situations that we'll be considering in this course. Okay. That's why STAN is such a big deal for us, why it has been a game changer for data analysis in psychology and in many other areas like linguistics and so on. All right, so for our purposes, it's just enough to know what sampling is, and I think I gave you a good intuition for that, right? And what you should do if you're technically very advanced, you should read this article by Neil 2011, which provides all the technical details on HMC. Michael Betancourt has a homepage which I've linked to here, which gives very good intuitions on HMC, and there's also a nice video by him that shows how to visualize HMC and how to understand it. On the homepage for this course, you will notice towards the bottom, I provided some links to some visualizations by people like Richard McElraith. They have provided some beautiful illustrations on how HMC works. So I advise you to study this later when you have more time. Right now, in this fast-moving one-week course, I think I can move pretty superficially through this Hamiltonian Monte Carlo approach and give you just a quick intuition for what the basic idea is. So as I said, the basic idea is that we are assuming that there's an ice puck moving over a frictionless surface. So for example, this upside down density PDF that we are thinking about, and this movement over the positions where the ice puck lands is going to give us samples from the distribution. Okay, that's the basic idea here, right? And so because we are imagining a physics kind of event, where you've got some movement of some physical object, right? So there's going to be some momentum associated with this object, and there's going to be some energy associated with this object, right? So basically the Hamiltonian Monte Carlo algorithm basically uses these properties of a moving ice puck to figure out, get samples from the distribution of interest. So I'm skipping all this because I really don't think that it's worth the time. In a longer course that we normally teach at Potsdam, we would spend a lot more time discussing this, but right now it's not really possible. So what I have provided you with is an implementation of the HMC algorithm for a simple example. I got this from the internet somewhere. And so basically, to make a long story short, you can define the function and then plot the, where are we? Sorry. I want to show you the samples. Yeah. So what you're seeing in red, you're seeing the true distribution that we're sampling from, and the bar plots, the histogram is actually showing you the samples that we got using HMC. Okay, so that's the end point of the whole sampling algorithm. But what I want to show you is that as the sampler is iterating through those 10,000 or whatever, 1,000, 2,000 iterations, what we can do when we finish sampling is that we can show something called a trace plot, which shows us over all the iterations what the trajectory of the sampler was, right? So remember that our goal usually is, if you have a distribution like this for a parameter like theta, we're getting samples like this here, right? So basically we could plot the samples that we get, the theta samples that we get, as a function of iterations. Okay, so this is iteration 1, iteration 2000, right? So I could get one sample here, so I come here, and then the next iteration I could get this sample, then I could get this sample, then I could get this sample, this sample, this sample, and so on. So if I just draw this plot, I will get something called a chain, right? So this basically shows me the transitions that the sampler took, as it was going through, and this is what you are seeing here. So typically what we will do is we will start the sampler at a particular random point, and then we will look at the chain graphically. And often what we will do is that we will run 4 such chains separately with different starting points. And our hope is that no matter where we start from in iteration 0, eventually each of the chains will be looking pretty similar, right? So what we say is that we have, if you have multiple chains that are overlapping with each other, we will often say that we have fat, hairy caterpillars, right? So that's a sign. When we see the chains overlapping, we call them fat, hairy caterpillars, and that's actually a sign that the chains are mixing nicely. That's the vocabulary that is used. And what that means is that no matter where you start from in each chain, you end up sampling from roughly the same space, right? So that's what we say when we say that the chains are mixing nicely. And you will see examples of this very soon when Bruno takes over this class. Okay, so typically, when we do our sampling, we will start with 4 different initial values and run 4 separate chains in parallel, and we will then draw them on top of each other, and you will see this overlap of all the 4 chains on top of each other. And that's a very characteristic shape that you will learn to recognize with experience. When you don't have mixing, you will have a situation like this, like one chain will go like this, the other chain will go off like this, another chain will go off like this, right? That's a bad situation, and that shows that your sampler is not mixing properly. There's something wrong with your model. You need to reparameterize it or do something to make it make the samples converge. Okay. All right. So that's basically the story with sampling, and I think we are now ready to start looking at some serious stuff involving Stan.